Okay, today what we're going to do is what I wanted to go over in Monday's class, which was canceled. What I want to do is just briefly kind of go over the assignment one, some of the answers for you in case you're confused. I'm not going to be able to go over these in class, and some of this material is likely to show up on the exam. So, excuse me. First question is, of course, about the dissociation constants with IgM and IgG. What I have here is written out as a rather long answer to this, so that you'll explain, so that it will be explained to you. But the bottom line is that you need to sort of remember back with your biochemistry, where the free energy of binding can be can be thought of as a dissociation constant. And so the free energy and binding sites to a surface, an antigen on a surface, would be additive. And so the individual monomers, for example, for the Fab fragments, which have one binding site, the individual monomer for IgM or IgG can have different dissociation constants. But if I take and if I add for an IgM, you have 10 of those binding sites, and I put them together, and they bind to a surface, then they're going to stick. The binding of that IgM molecule is going to be much higher than just for one molecule. You can sort of think of it in terms of, if I had one hand to grab onto something versus 10 hands, I could hold onto something much tighter if I had 10 hands, even though each hand has a weak interaction. Aggregately, they have 10. And so, the dissociation constants then are multiplicative, and so that's why you would get a higher binding affinity as you have more binders. The other thing too is that in this particular problem, you're thinking about binding to the surface of a bacterial membrane, and so therefore the antigen is going to be on the surface. It's going to be in a certain density on the surface, and therefore you're going to it's going to interact with the surface. It's not interacting with just free antigen floating around, and so therefore that's one of the reasons you also get a higher affinity, because you just have, once one arm binds, then the effectomolarities go way up, and you get an additive effect of each one of the dissociation constants binding to antigen on that surface. And so you can read through this answer, and I think that should be self-explanatory. The bottom line is that IgMs can have pretty high affinity, stick to bacteria pretty high, with high affinity, because they have more than one binding site. And generally, IgGs do have high affinity, but their binding sites have higher innate affinity and lower KDs than, for example, IgM binding sites. But they are bivalent, so therefore they need to have higher affinity. The second question had to do with the two IgGs isolated and found to bind to the diphtheria toxin, and they don't seem to interfere with one another. Here, the main point here is that the antigen determinants are not the same, and in fact, there's a term, they're not overlapping or self-reactive, and so they're non-overlapping, and so it's not binding to one part of the antigen determinant, another antibody is binding to another. They appear to be non-distinct antigen determinants on the antigen. And those differences, there are differences in the structure and composition of those variable regions of those antibodies are responsible for this difference. And so not only is the antigenic determinant sites different, but the binding sites for these two antibodies, their binding sites, the composition of their CDRs, and their composition of that binding site, the loops, and what's on those loops is going to be different as well. So in this case, what you would refer to this as a polyclonal. These are going to be polyclonal, right? Because they two antibodies that can bind to the same antigen, but they have different antigen determinants. Why are antigens better than why are proteins better antigens than sugars? We've gone over this before. There's proteins have a greater density, greater amount of functionality. There are 20 different amino acids, range of different potential chemical functionality. Can fold into a variety, enormous number of different structures, and provide a lot of different complexity things that can be recognized. Sugars are pretty complex too, and oligosaccharides are very complex too, but they have a fewer number of functional groups, hydroxyl groups, hydrogen bonding groups, and hydrophobic interactions from methylenes. And then also the diversity of their types of structures is not nearly as great as they are for proteins as well. So that's the main reason. We're going to see later why. There's another reason why they're more proteins are better antigens too, and that has to do with the way the adaptive immune response is generated. 4, this patient is found to be unable to produce IgA, and IgA is the main excreted antibody. There's a mistake here. That should be IgA, not IgG. So IgA is the main antibody excreted in the mucous membranes. Therefore, inability to produce IgA would make a person more prone to infections of the GI tract, respiratory tract, and urinary tract. So remember, it's IgA, not IgG. There's a mistake on here with regard to that on this answer right here. It's IgA. So if you don't produce any IgA, then you're going to be more prone to infections in these mucous membrane areas. 5, antibodies are structurally very sturdy. What are the 2 major types of secondary structures you find? Well, what you find is they're mainly made of the 2 most important are beta sheets and loops. And the beta sheets are for structural stability, the most stable secondary structures you find in proteins. And loops have flexibility, and they contain a variety of different shapes and conformations. And so those are the ones that are used for the binding pocket. That's why they're so important. So beta sheets and loops tend to be the most important structures that you find on antibodies. 6, why might a patient who has low neutrophil count be treated with GM-CSF but not M-CSF? Well, the bottom line is GM-CSF affects almost all the myeloid cells, including neutrophils, and it can be used to increase the number of those cells, as most importantly with neutrophils. Whereas M-CSF is really in that line. If you look at the chart, it's really only involved in the production of macrophages, and so would not be of any use for neutrophil generation of neutrophils. If you want to take a look at that chart and just look at the things and see which cytokines have unique effects and which ones have effects on a variety of different cells. And GM-CSF is one of those. 7, what are the key differences between how a member of the hematopoietin superfamily binds to its cytokine relative to TNF receptor? Well, the main difference is that hematopoietin receptors bind their respective cytokines by forming dimers of 2 homologous proteins. They come together to form the binding pocket which the cytokine binds into, and as we've gone over that before, and EPO, of course, EPO receptor is a good example of that. Whereas members of the TNF superfamily tend to bind the cytokines in monomers, and they tend to bind actually them more along one face of a monomer, or more of a specific face of the cytokine, which is amenable potentially to drug design. 8, erythropoietin is important in biotech drug. Why is it given for people with anemia who are anemic due to chronic kidney disease? Well, the main reason is that patients who are anemic have low hematocrit, therefore they have low number of lymphocytes, and EPO is used to treat patients that are anemic because it enhances, as you know from your chart, the proliferation and expansion of erythrocytes, and therefore will increase the hematocrit, and therefore relieves the anemia. So that's the reason that it is used. 9, this has to do with, again, the use of chemotherapy and radiation, why it's so toxic to bone marrow. The main issue here is really it's the toxicity to not just the progenitor cells, but really the pluripotent stem cells, because once you've wiped out the pluripotent stem cells, you can't have an immune system can't continue to produce cells, can't produce myeloid cells, can't produce the lymphoid cells, and so therefore your immune system will collapse and you become more susceptible to opportunistic infections. So that's one of the reasons. It's also one of the reasons when you do this, you can kill all the leukemia in the patient, supposedly, and then if you give a bone marrow transplant that is free of leukemia, it will repopulate the system and potentially could cure a patient of that. And that's a therapy that is used. Last question: why would a disease that led to destruction of the stromal cells result in an inability to produce B and T cells? The stromal cells are really kind of nurse cells. They're in the bone marrow, and what they do is they provide not only nutrients but cytokines and other things that really guide and control the growth and differentiation of the progenitor cells, the stem cells, progenitor cells, into the terminal cells that you want, the myeloid cells and lymphoid cells, and that goes for B and T cells. They are involved in that. So if you don't have the stromal cells, then you would expect those you would have if you didn't have the stromal cells, you would expect the loss of those cells and then also a collapse of the immune system. Okay, I think that's about it. I will I'll also post these answers as a PDF for you as well, and I'll make that correction on the slide where it was supposed to be IgA and IgG. Okay, all right. See you later. Take care.